So the simulator, flight simulation software is pretty straightforward, and here I'll show you as we're going here. Show you how it runs. There's a program in there, and it's basically updating every cycle, every computing cycle. Actually, I have to slow it down so that it's second by second. But every computing cycle, it goes through, and reduce contrast a little here. Maybe you can see it better. There we go. It goes through and it updates the status of the balloon. And starting from the top, we have here altitude, and right now the altitude is flight level 293. That means 29,300 feet. Now 29,458 feet. That number is increasing because the feet per minute, the ascent rate indicator, or the what's called the variometer, is telling us that we're ascending, and we're ascending at a rate of 1,100 feet per minute, roughly. There's a timer going up here, hours, minutes, and seconds. And there is here a buoyancy force indicator that tells me how many pounds the balloon is capable of bringing up versus my payload. Right now, balloon force is, or buoyancy force is 948 pounds. Sounds like I've got an alarm. The alarm is jettison fuel tank 1. It's just an indicator down here telling me jettison fuel tank 1. It'll turn off in a second. So my buoyancy force right now, the balloon is capable of holding, carrying 956 pounds. The payload is 570 pounds. And so as long as the buoyancy force indicator is above the payload, we're in good shape. That number, the buoyancy force, is calculated from a formula that looks at or considers all kinds of variables, about 15 different variables regarding atmospheric pressure, temperature, density, and so on, and compares it to the properties of the gas inside the balloon. And if the properties of the gas inside the balloon are sufficient, you are going to rise, and if they're deficient, you're going to sink. So we're here now looking at this ascent rate of around 1,100 feet per minute. That's pretty fast. Maybe I can get it around 700 to 900, but in a hot air balloon, 1,100 is pretty fast. This is a fuel counter. It's counting up, actually. I don't want to talk about that right now. This is going to help me estimate how much fuel I'll actually need to burn. OAT is a standard term. It's outside air temperature, and by the standard atmosphere model right now, at 31,000 feet, I should have a temperature of minus 32 Fahrenheit. That's OAT, outside air temperature. BET is balloon envelope temperature. It's 149 Celsius right now. Oxygen, kind of like fuel. I'm not really monitoring right now, not worrying about that. APSI is ambient per square inch. That's ambient pressure. And we have 6.3 pounds of pressure right now. APSI at sea level is about 14.7 pounds per square inch. So we're down to about 6 psi outside right now. Because of that lowered pressure at 32,000 feet, right here, I have an indicator that tells the minimum suit pressure. This is what the suit pressure should be set at. Right now it's 1, that's 1 psi. Suit at 32,000 feet would be set to 1 psi. That is determined by the pressure schedule that I've got, that I was showing in the previous video. That pressure schedule tells me what pressures I should have at different altitudes. These are a number of alarms down the side here, and basically, let's say I want to fire the burner, and let's say I want to increase my ascent rate. That's done by firing the burner, increasing the temperature, and decreasing the pressure inside the balloon envelope. Let's see what happens. So I'm firing that. And you can see that an alarm has come on now. This is the balloon envelope temperature alarm. I'm now at 164 degrees Celsius. That's too hot. And when you can burn a hole through the balloon envelope if you are too hot. So I've gone too high. I've increased my ascent rate to 1,400 feet per minute, but the temperature in the balloon envelope is dangerously high. I need to reduce that. One way to do it is to vent. And so down here I can vent gas from the balloon. That alarm is going to keep ringing until my envelope temperature comes down to below what I've set as the highest, which is 150. At 150, we're at 154, drop down, 151, 148, we're below the maximum operating temperature, and we're in good shape. The balloon envelope temperature alarm has turned off. 33,000 feet now, 33.8, so flight level 338, which is 33,800 feet. Flight level 338 in aviation terms. TTT, this is time to target. That's the target altitude, which is 50,000 feet. Right now it's 16 minutes. That's simply counting down. When we reverse and go down, this is time to ground, TTG, time to ground, how long it's going to be till we hit the ground or land at the given descent rate. Right now we're at ascent rate, and that blinker is showing me that we're ascending. When we go into descent, that lower blinker will be descending. During the simulations, then, the person on the radio here will be talking to me and telling me what suit pressure I should set, keeping me updated with our altitude and so on. A second computer will be showing me a few of the things that are indicated on this flight simulator, but those will be only the things that I would see in the balloon, and that's going to be altitude, my ascent or descent rate, APSI, and a couple of other things, but not quite all of this information. I'm reducing all of the automation on the entire project. I'm reducing all electronics as low as I can get. I don't like batteries. They fail every time at the worst possible moment. So I do have a battery, of course, on board, but I want to keep the use of the battery to an absolute minimum. And so I'm using entirely, or as much as I can, automatic controls and automatic indicators, for example, or mechanical, I should say. For example, the altimeters and the variometer on the balloon itself, they require no power. They simply sense what's going on in the atmosphere outside. But there is a place for electronics, but that's largely on the ground. Another thing that the person who's running this simulator can do during the simulations is, of course, they'll be talking with me on the radio, but there's also this interesting thing that I've built here, which is called the fail panel. And the fail panel, 5 ways to fail. At various times, during the simulations, I'll set this up into the program itself, but I want to be able to simulate systems failures. The few electrical systems that are on board could fail, and what do I do in the event of a failure? Well, I have to switch to a backup, or take certain courses of actions. And during simulations, a failure program will run, and it will, I don't know if I'll do it yet by random, I'm not sure how I'll do it. I won't know what failures are going to come up, though, during the test. But the person operating the simulator program and talking with me on the radio will be told every once in a while to fail a system. So they flip that switch, and it is connected to my electrics over here, and it'll fail a system over there. Well, suddenly I've got a failure, and now I've got to react in the proper way. Some failures will have, I guess all of them should have, a standardized set of procedures for if you get a failure of type 1, 2, 3, whatever the failure is, then you go into a procedure to deal specifically with that failure. So all of this is being integrated, like I was saying in the last video. I'm integrating the simulation system, all of that, with the hardware, and then the actual procedures. All of that is starting to come together. And it's going to take a lot of simulated flights. One of the flights I want to do, a simulated flight, will be with a person running this machine and talking with me on the radio, visually cut off from me with a visual barrier. I can't see them, they can't see me. They can see me through a camera that will be pointing there, and it's displayed on this other computer. They can see me kind of through that, but I want to be in the situation where visually I'm cut off from everything else. But there'll be a person here in Portland. However, there'll also be a person talking from Los Angeles. This is John Haslett, a buddy of mine in expeditions for years now. He'll be communicating by radio with the person operating this thing. And he'll be flight command, basically making the command decisions of whether we proceed, ascent rates and descent rates and so on. He'll communicate those to the simulator person here who is running this part, and they will then actuate or communicate things to me, and will therefore simulate basically, to a degree, the issues of communication and so on that will actually happen during flights. So those are some of the issues I'm starting to work on. To me, all very exciting stuff.